So maybe can you? Okay. Okay. So today we will have a special guest, Professor Giga and Professor Ishii. So before that talk of show, I asked Professor Giga and Professor Ishii to give a short greeting.
Oh,
Okay,
comment.
please.
Okay. Okay. First of all, it is my great honor to have a chance to participate this very nice meeting. Although I have to leave within 20 minutes, but I look forward to the activity of this series of lectures.
Yes,
Okay. Thank you very much for inviting me to this meeting.
thank you. Okay, so please, Professor Ishii.
I, I'm very happy to join this meeting. Thank you for invitation to this meeting, and I hope I will continue to join
Yeah, this
your
is great.
seminar.
Yeah, this is great. So yes, I
Thank you
will.
very much.
Thank you.
Okay, thank you so much. Okay, so now it's time to start a short talk. So can you show
Okay.
your slide? I still can't see your slide. Everybody, other people. Okay, now I can see.
You see the slide?
Good. Okay, so it's great pleasure to have a show today. So he is going to talk about his recent work with Professor Giga. The title will be is large time behavior of exponential surface diffusion flows on the whole space. Okay, please.
Thank you for your kind introduction. Thank also Professor Mitake and Professor Tran and for inviting me this great meeting and giving me a great opportunity to talk with you, the whole participant. As in the title, I'm going to talk about some large time behavior of exponential surface diffusion flows on a, or a graph on the function of for real line. Let me start the talk. First, as the exponential surface diffusion flow is a kind of uncommon equation, I'm going to give some explanation. We consider the evaluation of the curve on the real plane described by the v equals to the second derivative by the curvature, the arc length parameter of the f of the minus the curvature. So this is
So I think you have
this.
some problem. I can't listen to your voice now.
Sorry, can you hear me?
Yeah, yeah. Now, yes, I can hear.
あ、そうです。This equation. So, as I already said, the v is the normal velocity of the curve, and the s is described denotes the arc length parameter for the curve, and the kappa denotes the curvature of the graph. So, and most importantly, and most peculiar for this matter in this equation, the f is the given increasing function on a for line. As in the title, the typical example of the curvature nonlinearity f is the exponential one. That is the v equals to the second derivative by the arc length parameter of the exponential of minus the curvature. In this case, of course, the curvature nonlinearity f is the exponential function. Compare with this equation with what we usually call the surface diffusion flow, that is the v equals minus to the derivative, second derivative by s of the curvature. In this case, of course, the curvature nonlinearity f is a simple f r equals r. So for convenience, we call this equation a conventional surface diffusion flow. Let me explain why we want to consider this equation. The exponential surface diffusion flow is proposed by Martin, who is a material scientist, but as a model of evolution of grain boundaries by the physical process called relaxation process. For example, the grain of gold at low temperature is known to follow the relaxation process. I also refer the paper by Kong and Magretis because the original paper by Murray implicitly uses the approximation of exponential by by fr equal r. So I prefer the one paper that explicitly use the exponential nonlinearity. Of course, if curvature is very small, then exponential function is approximated by this function. So the exponential surface diffusion flow is considered to be close to the conventional surface diffusion flow. Let me explain the derivation of the model. The first setting is that there's some grain of the material and with the boundary denoted by gamma. I assumed there are atoms in the grain boundaries, but the distribution of the atoms on grain boundary gamma is not uniform. That is in somewhere there are many atoms, and while there are some other places there are few atoms. And we assume that the atom can move on the grain boundary. And the movement of the grain boundary, it follows the usual flux law. That is, the flux of the atom is proportional to the gradient of the density of the atom. Also, the grain boundary moves as the atom, the distribution of the atom changes. So we assume that the normal velocity of the grain boundary is proportional to the increasing rate of the atom per area. That is a minus divergence of the atom flux. So these two laws connect the normal velocity with the atom density. So we need one more thing that connects the atom density with some geometric data of the grain boundary. A law that plays this role is called the Gibbs-Thompson law. This connects to the atom density with some surface energy. In many settings, In particular, at the isotropic settings, the surface energy refers the mean curvature of the grain boundary. So the Gibbs-Thomson law is expressed by logarithm of the atom density is proportional to the mean curvature. Summarizing these laws, we arrive at the resulting equation that is the normal velocity v is proportional to the Laplace Bernoulli of the exponential minus beta kappa. This is the original exponential surface diffusion flow. Of course, we can erase these constants by some scale change. So we can consider this equation as we call the Laplace Bernoulli of exponential minus kappa. Of course, in the one-dimensional curve setting, the Laplace Bernoulli is the second derivative of by the curve arc length parameter. So we can consider this equation as the vehicle second derivative by the arc s of f minus kappa, where f is the exponential function. In all things what follows, we consider the surface diffusion flows for a graph on the function for line. So instead of gamma t, we consider the function u of xt. Of course, for graph of functions, the velocity of the normal velocity of the graph and the parameter derivative for a curve and the curvature of graph curves are expressed by this formula. So substituting this formula for the exponential surface diffusion flow, we can convert the exponential surface diffusion flow to a graphical form. So instead of the geometric evolution, we suppose consider this evolution equation on the whole line. Let me explain our goal. As in the title, our goal is to investigate the large-time behavior of the global in-time solution to the exponential surface diffusion flow. However, for the exponential surface diffusion flow, even the existence of the global in-time solution is not known, we have to first consider the solvability problem for the global this exponential surface diffusion flow. So as a result, we can just justify the approximation by the conventional surface diffusion flow for the exponential surface diffusion flow from the viewpoint of the large time behavior of the grain boundary. So before talking about the exponential surface diffusion flow, let me explain some known results for the conventional surface diffusion flow. Of course, the conventional surface diffusion flow of the graphical form is this evolution equation. That is the general exponential surface diffusion flow with the curvature nonlinearity f is if r equals r. So the first important thing to remark is the scale invariance. This conventional surface diffusion flow has a scale inverse property by this scaling. So in things what follows, the scale invariance plays a very important role. First remarkable result is proposed by Koch and Lam in the 2011, 2012. They proved that the unique existence of the global in time smooth solutions to the conventional surface diffusion flow of the graphical form, and the assumption that the slope of the initial value is very small. I remarked that the results does not require any smoothness of the initial value, and we can interpret it this condition in the weak derivative sense. So the user is only required to be a ellipsis. I also mentioned the scale invariance of this condition. So of course the ellipsis, the homogeneous ellipsis space is an invariant space by this scaling. So this condition is scale invariant. Also, they worked on the space of the uniformly local Sobolev type with the invariance under this scaling. So their whole setting of problems as invariant is the scaling of the conventional surface diffusion flow. So in the conclusion for the consequence for the result by Koch and Lam, we can choose the homogeneous initial datum, that is the U0 equal epsilon times the absolute value of space of the x. So result by Koch and Lam, the conventional surface diffusion flow possesses a unique solution that is denoted by capital U of epsilon if the constant epsilon is very small. The uniqueness matters. Since the homogeneous initial datum is invariant under the scaling, the capital U epsilon sigma, that is the scaled function of the solution U epsilon, is also a solution for the conventional surface diffusion flow with this initial value. So uniqueness says that the scaled function of the U epsilon, the capital U of epsilon, is equal to the original U epsilon for any sigma. So this solution is called self-similar solution for the conventional surface diffusion flow. So as a conclusion, the result by Koch and Lam says that there are a non-trivial self-similar solution with a small slope. I also hear mention the paper by Giga and Miyakawa. The first of the author is the special guest of this talk. They construct of the self-similar solution in the vortex equation that is formally equivalent to the Navier-Stokes equation with this spirit. That is the solving problem in the scale invariant setting. So this result can be said to inherits the spirit of Gien and Miyakawa. Later on, Do and Ip in 2023 proves the large-time behavior of the surface diffusion flow with a general small initial data. They prove that if the slope of the initial data is small and it is close to the homogeneous data in the sense of the difference of the initial data and the some homogeneous data is bounded, then the scaled function of the solution is close to the self-similar profile of the conventional surface diffusion flow in the sense of the local uniform convergence. So in other words, the result means the stability of the small non-trivial self-similar profile of the conventional surface diffusion flow. Their method is based on obtaining a decay estimate of the solution of the conventional surface diffusion flow of the scale invariant type, and the use of the R-square R-square theorem to capture some limited function, and so of course since the limit function satisfies the conventional surface diffusion flow equation, and the initial data is the homogeneous one, so the limit function is exactly the U epsilon. So by the uniqueness of the limit of the subsequence, that the profile is, so we can say that the solution of the profile solution it converges to the self-similar profile without taking any subsequence. I also refer to the books by 2 Gigas that the performs a similar type argument for the Navier-Stokes equations. So we go back to the exponential surface diffusion flow. As the exponential surface diffusion flow is expected to be approximated by the convolutional surface diffusion flow if the curvature is very small. So we expect that the second derivative of the height function u is very small. The behavior of the solution of the exponential surface diffusion flow is similar to that of solution of the conventional surface diffusion flow. So we expect that the scaled function of the solution of the exponential surface diffusion flow is close to the self-similar profile of the conventional surface diffusion flow if the initial datum U0 is close to the homogeneous data as the space infinity. It is also easy to check that if the limit function of the scale solution of the exponential surface diffusion exists in some good space, the profile function U satisfies the conventional surface diffusion flow, and homogeneous initial datum. So the limit profile of U it should be the self-similar profile for the conventional surface diffusion flow. But there remains the problem of the existence of the limit. So we need some arguments for this limit problem. So I also explained the difficulty of the general surface diffusion flows. First, of course, as this equation is fourth order, so this equation cannot have any comparison properties, unlike the second order equation. So, in fact, for the exponential mean curvature flow that is described by V equals to that is described by the normal velocity equals to 1 minus exponential minus kappa. There are some results for the limit profile. For example, Hamamuki by 2014 that states that converges to the self-similar profile for the usual mean curvature flow. But his result totally relies on the comparison principle. We cannot refer his result for the exponential surface diffusion flows. Also, we cannot access any energy monotonicity for the surface diffusion flow. In fact, if the grain boundary is bounded, we can consider some energy that decreases along the exponential surface diffusion flow. But in our setting, since the graph of equation is unbounded, so if we try to consider energy, the energy is infinity. So so this energy makes no sense. So we cannot access any energy monotonicity for this equation. The third difficulty of this problem is peculiar for the exponential surface diffusion flow. This is unlike the scale invariant settings, such as in the Koch-Lammer dweep, we cannot rely on the scale invariance when we choose the norms which we work well, so on, because of the curvature nonlinearity. So, of course, this is due to the lack of scale invariance and the necessity of the controlling the curvature due to because the typical example of the curvature nonlinearity is exponential. That is a very extreme nonlinearity. So we consider that we need a pointwise control for the curvature. So while the scale invariant norm, in fact, does not control in the curvature in pointwise sense. So we can reconsider the norm to work on. These are difficulties of the exponential surface diffusion flow. Keeping these difficulties in mind, I explain our main results for the exponential surface diffusion flow. First theorem states the global existence of the exponential surface diffusion flow with the small initial data. We assume that the slope of the initial data and the the curvature of the initial data are both small in the pointwise sense. Then the exponential surface diffusion flow possesses a unique smooth global in-time solution U. Furthermore, the U satisfies this pointwise estimate for the derivative, but I forgot to add this extra matter. This is a mistake. So the correct thing is this power of t and times the 1 plus t time to the power of minus 1 over 4. If the k and l are not 0, so I remarked that we allowed the initial data to be unbounded because we only control the slope and the curvature. So this profile is possible. So we cannot control u in the pointwise sense. So we only control the derivatives of u. The second theorem is the most important matter that states the large time behavior of the exponential surface diffusion flow. In addition to the smallness assumptions on the theorem 1, we assume that the initial datum u0 is close to the homogeneous initial data at the space infinity. Then the scaled solution is converges to the some function u epsilon in local r times 0 to infinity. That means that the uniform convergence of each compact set of this set, and also the profile function derivatives of profile functions converge to the derivatives of the u epsilon in the uniformly for each compact sets of r times the open interval 0 infinity. So of course the function u epsilon is a unique self-similar solution to the conventional surface diffusion flow with the homogeneous initial data. I'm going to add some remarks on this main result. Our main result implies that if the slope and curvature, as I already said, the slope and curvature of the initial datum are sufficiently small, then the solution of the exponential surface diffusion flow behaves like the solutions of the conventional surface diffusion flow. In this sense, our result justifies the approximation of the exponential surface diffusion flow by a usual conventional surface diffusion flow. So in this sense, our result matches the first goal of our consideration. In do and if that is, of course, consider the conventional surface diffusion flow, also considered a global convergence of the scale solution to the self-similar profile with an additional spatial decay assumption that control the weighted LNPT norm of the difference of the initial data and the homogeneous one. Although we expect that the similar analysis is possible and we can obtain the global convergence of the to the self-similar profile for exponential surface diffusion flow, we will not consider this type analysis in this time. Also, our analysis can be applied to the exponential surface diffusion flow for a multi-dimensional graph, such as a real green boundaries that is the two-dimensional curve, two-dimensional surface. So, of course, as in the derivation, I explained that this problem can be considered in the multidimensional space, and the resulting equation is one. Here, a P of gradient of U is this matrix. So this is also for the parabolic equation, and in fact, we can consider this equation in the same analysis as in the exponential surface diffusion flow on the whole line. But for simplicity, we restrict our consideration to the one-dimensional. I explained the strategy of the proof. As in the do and if result, obtaining the decay estimate of this type is essential. But this is also wrong. This one should be removed. This estimate should be the t to the power of minus k plus 4 to 4L over 4. So this estimate is invariant under the scaling for the conventional surface diffusion flow, and we arrived at the existence of the limit function. To prove the great global in time existence, also this estimate is essential. Our strategy of proving the global time in time existence is to extend the local time in time solution by this uniform estimate. Also, the use of as I already said, the use of the Euler theorem enables us to obtain a local limit of the scaled function of the solution to the exponential surface diffusion flow. That is, of course, the self-similar profile of the conventional surface diffusion flow. Next, I explain strategy for the decay estimate for the exponential surface diffusion flow. Instead of considering the solution U directly, we consider the spatial derivative of the solution that is denoted by V. So for the equation V, the equation for the spatial derivative V of the U is obtained by differentiating by x the exponential surface diffusion flow and given by this form. To obtain this estimate, we rewrite the equation in the form the perturbation of from the biharmonic heat equation, and we can apply the analysis for biharmonic heat equation. Here the alpha and f are coefficient functions that depends on the solution. So this equation is still linear. And we try to use a decay estimate for a linear parabolic equation that is expressed by the perturbation from the biharmonic heat equation of this form. But this is not simple. We first explain what we have to do. First, because for the exponential surface diffusion flow, even then the local in-time solution existence is not known, we have to establish first the local in-time existence of a solution. But in fact, this is somewhat standard for in the case linear parabolic theory of the case linear parabolic equation. So we omit here the proof of the local existence of a solution. We just admit it. Also, the short time estimate of the solution of the exponential surface diffusion flow is essential. In the second step, we establish the linear decay estimate for the exponential surface diffusion flow of this equation. So, and also we apply the elementary estimates for the coefficient functions so that we can use our linear decay estimate to the exponential surface diffusion flow. As a result, we try to obtain an estimate of the form that if the norm of the solution is very small, the solution norm is more small. And combining the existence in the short time and the trapping argument, we can obtain the whole decay estimate for the exponential surface diffusion flow. But as I said, the thing is not simple. We have to consider what are appropriate norm for the exponential surface diffusion flow. Unlike the conventional surface diffusion flows and many other equations, the scale invariance property will not help us to choose the norm. Also, the estimates of the derivatives of these coefficient functions are very complicated and also very delicate because of the curvature nonlinearity of prime. So as we differentiate these functions, the derivative of curvatures and some derivative, many things appear. So we can and also these quantities may take extreme behavior. So we have to be very careful for these estimates. The key matter of to deal with this equation is this difficulty is the newly introduced scale parabolic Hilda norms. This resembles the usual Hilda norm. though the form is very complicated, but this is these terms are standard. But we add the power of the interval of the time interval, so that this norm has a scale invariance property. Of course, if we replace the b minus a by 1, this norm becomes a usual parabolic Hilbert norms that the Schauder theory is performed. I explain some properties for these scaled norms. The first, as I already said, the
So,
scaled.
sorry for interrupting you, but maybe for this, I think you can just explain some idea, quickly.
Oh, okay.
Yeah,
Oh, sorry,
because,
sorry. I
no,
I
we
used
still
too
have
much
time.
time. Sorry, sorry.
No, we still have time, but maybe for this, maybe you can just explain some idea and
Okay, okay.
not going to the very detail
Okay,
because
okay.
yeah.
So our idea is the use of the scale invariance to transplant the simple estimate, simple estimate of the composition and products without expanding them. So, and in the constant without depending on the time interval. So these are resulting estimates. First, the product estimate is, as usual, the norm of the product is controlled by the product of norms with a constant not depending on b minus a. Also, the composition estimate is of the usual type, both without a constant dependence on b minus a. These things are actually essential. Secondly, we also transplant the parabolic estimates for the delta norms to the scaled Hilbert norms. As usual, we use this notation for the biharmonic heat flow. So we can transplant the user parabolic estimate to using a scale invariance property, and we obtain the following parabolic estimates for the scale Hilbert norm. Firstly, a usual smoothing property of the biharmonic heat flow becomes this form. So this is simply the scale Hilbert norm of the t on the time interval distant to 0 is controlled by the initial data. So this also, of course, this resembles the usual smoothing estimates. We also transplant the Schauder estimate for the scaled parabolic Hilbert norms. So for the Duhamel type function of this form, that we can estimate this norm by the Hilbert norm of the external force with a constant proportional to the time interval. This is also essential. These are also essential estimates. using the scale invariant, the scaled header norms, we transplant the weighthead. We could we choose the norm one that we will work on as that this is weighted form. This norm is asymptotically scale invariant as a t equals to infinity as the usual scaling. That is also the second term. In particular, this part makes the derivative of the solution of the v uniformly bounded and enables us to deal with the curvature nonlinearity. In particular, the control of the norm zkt implies that this type of pointwise estimate for the solution of the v. So if we control the zkt norm for the solutions of the exponential surface diffusion flow, our goal is achieved. So this type of norm estimate is adequate for our scheme. The adopting the scaled and weighted parabolic norm of these forms has these advantage. These norms enables us to obtain asymptotically self-similar scale invariant estimates of the derivative of the coincidence function without expanding them. So if we try to obtain this type of estimate without these norms, we have to derivative these times, these equations, so many times. So I'm too lazy to do that, but so I did not do that. Also, the invariance of the constant, the independence of the constant of of mentioned estimates enables us to deal with the curvature nonlinearity with a unified calculation. So that we do not need any special calculation to deal with the curvature nonlinearity with these our norms. Grabbing these norms, we started with the linear decay estimates for this equation.
Okay, so
Yes.
I think it's time is running, so maybe you can very quickly go
Okay.
through and maybe summarize.
Right.
You
Yes,
have
sir.
some section of the conclusion.
Okay. So
And after your talk, we will have a time to chat, to ask a question formally. And after that, we will have some informal discussion. So maybe for that time, you can explain more.
Okay. So our linear decay estimate is that this is the control of the perturbation is very small, and so we can control the Z14 of V by these quantities. Our proof of the decay estimate is done by we first consider the biharmonic heat equation by this decomposition, and the use of the smoothing and the shadow estimates we can estimate these quantities by the simple integrals. And we arrived at the desired estimate for in the case alpha equals to 0. In general small alpha, what we have to do is to control the alpha times Vxx by this norm. Again, we do not have to expand the second derivatives of this equation. Just we apply the product estimates for the scale invariant norms to arrive at the required estimate. So we can arrive at this estimate. Yes, the delta is very small. We can absorb this term to the left-hand side, and we arrive at this estimate. So this is our linear equation. Next, we do a nonlinear decay estimate by estimate alpha and f. For simplicity, instead of the exponential surface diffusion flow, we consider this model equation. Although this equation is very simple, but do not lose the essence of our estimates. This is a recall of our scheme, so we skip it. As a result, of this estimate, we arrive at the desired decay estimate for the estimate equation. And at once, we can obtain the global in-time existence of the equation. The nonlinear estimate for the alpha and f are now very simple. The only thing we have to do is to apply these estimates for the product and the composition estimate to on the form of these forms. This very, very simple estimate gives adequate estimate for the use of the linear decay estimate. So these very simple calculation yields the desired estimate. Also, as I said, although the original problem is more complicated, but the essence is the same. But we have to estimate the curvature first, but it is also very easy. Also, I remarked that the V is the derivative of the solution of the exponential surface diffusion flow. The time derivative of the U is yet to estimate. This can be done by this formula. So it is also very easy. Also, the further use of the shadow estimates and the bootstrap argument is the higher regularity of the solution solution, but we do not touch it. Finally, the use of these estimates enables us to obtain a convergence profile of the scale solution. As I said, by this estimate, we can obtain the uniform estimate for the scale solutions. Also, this estimate implies that the uniform equicontinuity estimate for the scale solution. So the Ascoli-Archer theorem tells us that for some subsequence that is denoted as sigma n, there is some limit function u in this space. It is, as I said, it is easy to check that the u satisfies the limit equation, that is a conventional surface diffusion equation, and the solution u0 furthermore, the initial value inside datum u0 satisfies the resembling to the homogeneous initial data as a space infinity. The limit function satisfies this initial condition. So, by Koharam, the u is exactly the unique similar profile epsilon, and the uniqueness of the limit profile implies the whole convergence in the u sigma to the u of epsilon.
Okay,
So we can arrive there.
sure. Okay, this is great.
Yes, I'm
Okay.
sorry for my poor time control, but thank you for your kind attention.
Okay, thanks a lot.
I think it's way over time, so we should stop and then we do question and discussion after this because it's already way over time.
Okay, okay. So, okay, so Han, please stop the recording.
Okay, so thank you, Sho. Let me stop the recording and then we do informal discussion.